bipolar junction transistors or BJTs. What are BJTs? In terms of structure, this is internal structure BJT or bipolar junction transistor. This is not drawn to scale actually. Dili but pasabot nga kung yani ka baga ang N nga semiconductor material nga na po kabaga ang P, no? So dili na siya. This is just for visualization purposes. Hundreds of times larger man I think ang N-type material kaysa sa P-type material sa BJT. So dili siguro nga ni yun in actual, no? So again, this is just to visualize that a BJT is sort of like, as what the video said earlier, sort of like a sandwiched na semiconductor material. So we have two flavors also for the BJT. We have the NPN and PNP. Depende sa internal composition sa itong BJT. So if NPN, P-type material is sandwiched by two N-type materials, and the same gapon sa PNP. An N-type material is sandwiched between two P-type materials. So our BJT has three terminals, namely the collector, the base, and the emitter. Okay. So unlike the diode, which only has two terminals, namely the cathode and the anode, ang atong BJT has three. So it's better now nga i-memorize na ninyo the collector, the base, and the emitter. So whether it is an NPN or a PNP BJT, magining tulo. The collector, the base, and the emitter. So ang nasandwich sa tunga, connected dito ang base na terminal. No? Notice sa atong slide. So base, ginasapirme sa tunga. Okay? Conventionally, kung magdota o normally kung magdota BJT, ang upper na terminal, that would be the collector. No? So nasa taas ang collector. Although pwede magyapon nga ang emitter nasa taas. Pero for starters, usually ang nasa taas ang collector. And nasa silong ang emitter. So yeah, this is what a BJT should look like kung atong i-slice cross-sectionally. But kung mag-draw circuits, di ba nato ginadlo ang BJTs? We use symbols such as this one. So this is a symbol for a BJT. Actually, this is the PNP na BJT. Back lang to this first slide. The BJT has three regions called no, I don't sabi. I think ang diligid region ang emitter, base, and collector, but these are three terminals. I think dapat ang proper na term no? Three terminals na connected sa katong regions. No? The two N regions and one P region for the NPN. Between the regions are junctions, as indicated. The base is the thin, lightly doped region compared to the heavily doped emitter and moderately doped collector. So in terms of doping, ang pinaka-heavily doped is ang emitter, no? The heavily doped emitter. And the moderately doped collector. Have that in mind lang. So iyahang schematic symbol is this. For the NPN, mas better siya magdota na og vertical line and mag-connect og wire. Okay? So this would be our base, B. Then mag-draw tag duha ka diagonal line na nakaslant like that. Okay? And ano yung mga terminal. Okay? So either aning duha is the collector and the emitter. So which is which? Kung asa nakabutang ang arrow, muna siyang emitter. kung asa ang arrow. Okay? And the other one is the collector. So for the PNP, same gyapon, dotag vertical line. Kung asa ang vertical line, muna siya ang base. Dotag ka diagonal line. So pwede kaniyang collector, kani gyapon ang emitter. Kung asa ang arrow mo ang emitter. So for the PNP, the arrow is pointing inward. Okay? Or naiuban nga duol gid ni sa vertical nga line. Apoy uban nga ga-draw og circle, no? I-encircle ang symbol for the transistor, no? Pwede gyapon nga na. Pwede wala circle, pwede na. Yung ang important dire class isang arrow, no? Kung asang arrow mo gitong emitter. Okay? So ang arrow ang ga-determine kung asa ang emitter and vice versa. Okay? So that's the symbol for our transistor or for our bipolar junction transistor. PNP and NPN. Mostly siguro itong gamiton is ang NPN. For the remainder of the discussion, NPN atong flavor of use sa atong BJT. Ang PNP, usay naman, no? Maka-create na mga taog mga useful applications using only the NPN. Pero we'll learn later siguro na wala gid kaayoy dako nga difference with regard to the PNP and NPN. So yeah, NPN atong usually gamitan. So in normal operation, the base emitter is forward bias and the base collector is reverse bias. So what does that mean? So invoke na walik ang NPN nga transistor, NPN nga BJT. So kung asa ang arrow mo ang emitter, collector, base. Now we have we have 3 terminals. We also have 3 sinatawag na to ganian pairs of regions. Region lang sa gyapon, no, atong nga term. So napo tay 3 pairs of region. We have the collector emitter region, no? CE. We have the collector base region here, and we have the base emitter region, BE. These regions are the regions between the terminals, no? Di mo sila lisod yun timan-an, no? Kung bakit ka sa atong kuan sandwich, so muna ang CB region or collector base region, this one. Ang collector emitter or CE region is kani, and ang BE region or base emitter is this one. Just remember na we're not only dealing with the terminals individually, no? Not only the collector terminal, the base terminal, and the emitter terminal, but also the regions in between those terminals, namely the collector base terminal, the collector base region, the base emitter region, and the collector emitter region. So diha pod actually magikan ang atong mga gina-measure na electrical parameters, no? So we have 2 electrical parameters nga ato usually gina-measure, di ba? We have currents and voltages. Okay. We have currents and voltages. Okay. So we have three main transistor currents na atong gina-measure. Current going through the emitter, the collector, and the base. So we have current I, IC, current IE, and current IB. So natin tulo ka current. So ning erase na sa siguro. Bike na ako na later. So asa man nato makita ng tulo ka current. There's current flowing inside the base terminal, no? Let's call that IB. There's also the current flowing in the collector. Let's call that one IC. And napoy current nga ga-flow out sa emitter. So ato ni visualize ang ga-flow sa emitter is gikan sa transistor mismo pagawas. Okay? Pagawas siya. So yan na lang akong draw IE. Okay? So those are the three transistor currents, IB, IC, and IE. So about for the voltages. Okay. So katong mga regions earlier, ako na-mention. The region between the collector and the base terminal, CB. So VCB. Napoy voltage between the base and the emitter. Let's call that one VBE. VBE. And the voltage between the collector and the emitter. VCE. Mga three currents and three voltages. Basta voltage, pair siya of terminals. It's either VCB, VBE, and VCE. Wala na yung significance ng color na ako. So, paano na siya. Yeah. So back to this slide. In normal operation, the base emitter. So again, kung pair gani, pasabot na is voltage. Okay. So the base emitter is forward biased and the base collector is reverse biased. So we have an idea na ang base emitter is positive iyahang orientation, no? Kay forward bias man. Marugod gyapon diode. Well, exactly like the diode gid ay. And the base collector is reverse biased, no? So negative yung orientation. In normal operation, yeah, let's replace normal with as an amplifier, no? Normal operation magyapon ng switch. Pero yung ginapasabot dili is kung ang base emitter is forward bias, kung base collector is reversed, amplifier gina siya. No? So that's not to say nga ang BJT as switch dili lugar normal. No? So normal magyapon to. So normal in a sense na use as an amplifier. So for the NPN type shown, the collector is more positive than the base. Because sa visual na to is kuan man, no? PNP man eh. Either way, whether again there's no difference man between the PNP and NPN in terms of operation. So still, the base emitter should be forward biased, no? And the base collector is reverse biased. So no need to actually memorize good all of this. Kailangan nato i-familiarize lang ang mga terms. The deduction of the conventional current is the deduction of the arrow, the emitter terminal. So for the PNP and NPN. Focus lang sa NPN para masabta nato ang kaniyang concept. No? So we already defined the transistor currents as IC, IB, and IE. IC is the current flowing into the transistor. Di ba? Pasulod siya. Okay? So, pasulod na siya. Si base, pasulod gapon. Pasulod siya sa transistor. Si IE, ang gikan sa sulod, pagawas. So, we have our first very important relationship that relates the transistor currents. Kani siguro kinahanglan natin i-memorize. Formula number 1. IE is always equal to IB by virtue of KCL, no? Kirchhoff's current law, IC plus IB. This holds true whether PNP or NPN. Notice sa PNP, no? Although si IE kay pasulod, or si IC is pagawas man, same with si IB. No? So, pasulod si IE, pagawas both si IB ug IC. But still, if we'll formulate a KCL equation based on it, it's still IE is equal to IC plus IB. No? So whether PNP or NPN, mo gid ang formula na mag-define sa relationship sa transistor currents. Okay? IE is equal to IC plus IB. So the direction of the conventional current is in the direction of the arrow of the emitter terminal. In the direction of the arrow of the emitter terminal. So kung asang arrow sa emitter terminal, dito ang direction ni IE. And if we know what is the direction of IE, we'll know what's the direction of the other two currents. So before I proceed, any questions? Am I going too fast or nabuhay pangutana? Is everything clear so far? So on silence means yes. Okay, proceed ko. BJT characteristics. Okay. Kulang man yung visual. So we have 4 regions of operation for the BJT. Wala din ang isa, no? So let's pick a slide. Okay, the cutoff. So we have 3 regions of operation for the BJT based sa characteristic curve. So we call this one the same sa diode as the characteristic curve. Okay, so BJT characteristic curve. Now, unlike the diode and the passive devices like resistor, na ang characteristic curve could be defined by only voltage and current relationship, di ba? O mani ang characteristic curves at ng diode previously. Sa BJT, we have 3 sets of characteristic curves. So for here, we'll only focus on the characteristic curve of VCE versus IC. No? So ang x-axis is VCE, the voltage across the collector and the emitter nga region. This one here, maning VCE, and the current IC, current coming into the collector. So VCE versus IC. So for this characteristic curve, we have actually 4 regions of operation. Ang isa wala na mention today. We also have the cutoff region. So what is the active region? Any value, no? So after designing the circuit, no, after building the circuit, we use our tools to measure VCE. Let's say, for example, VCE is somewhere here. No? Good time mag-plot up ng line. VCE is somewhere here. Let's just say that is 5 volts. And we have IC equal to, let's say, 5 milliamperes gyapon. So, plot na to diha. Asa ilang intersection. So, nadire. Okay, so na ang intersection point. We call that one the Q point or quiescent point. Wherever the Q point is located sa characteristic curve, that is the operation of the transistor or of the BJT. Okay? So it could be either it could be located in either 4 regions. Sa kaninga example nako, the Q point is located on the active region. It could also be located on the saturation region or on the cutoff region or in the breakdown region. Okay. So if the Q point is located past this imaginary line, no, kanang red dotted line. Let's say, for example, atong Q point is na adire. After plotting the voltage across CE and IC, no? So nadiha kibali, let's say for example ang atong Q point na siya sa breakdown region, no? So sa may tabo sa atong transistor, so mag-breakdown siya, no? Mag-go busted atong transistor. We don't want that, no? So we want our transistor below this dotted red line, no? Below the breakdown region, at least the active region. So if our transistor has a very low na current, very low current, meaning, let's say for example, na adire, yet very high voltage, so na adire, asa ila intersection, nalapod somewhere diha, meaning nasa cutoff region. Or kung opposite pod, what if it has a very low voltage and very high current, 5 milliamps gyapon, let's say for example. So ilang intersection is kani, that's our Q point, na siya sa saturation region. Okay? Pero if perfectly balanced ang atong Q point, sakto lang, nga voltage across CE and sakto lang pod nga collector current, so na siya sa kani akong example, somewhere in between, so na siya sa active region. Okay? So the wherever the Q point is on the characteristic curve, that defines the actual application of our transistor or our BJT. So if you remember ganiya sa video, the transistor has only 2 lang yun. There are only 2 na functions or operations. Either it could act as an amplifier, so an application, either amplifier or switch. Nalang gid ana. Okay? So the transistor, what if breakdown lugar? Gawa na siya, so di na siya magamit, no? So na siya application. Pero mo gid na siya duha, no? These are the only 2 functions of our transistor, either amplifier or switch. Mo lang gid na. So what if lugar, sir, na siya sa sulod sa gadget nato, na siya sa sulod sa laptop or sa cellphone as transistor that makes up the microprocessors. No? So those transistors are acting as switches. No? What if lugar sir sa mga oscillators? Oscillators nga naa sa mga communication circuits. No? So basically, those transistors are acting as amplifiers. No? So bisan unsa pa na nga specific application, oscillators, filters, so pa ba? Sa instrumentation circuits, nalagid na pwede lagi na siya mag-classify either of these two, amplifier or switch. So kung amplifier siya, meaning iyang Q point is somewhere in the middle of the characteristic curve. If switch siya, the Q point switches no between saturation and cutoff region. That's why switch ang tawag, because baylo-baylo siya, magbalin siya from saturation to cutoff to saturation again, vice versa, so on and so forth. So switch ang tawag, no? Mag-switch siya. So when the BJT is in the active region, it acts as an amplifier. No? So na siya sa active region. It's not difficult to remember. As mas letter A, no? Amplifier, active, amplifier. Meaning, si collector, si base emitter is forward bias. Okay? Whereas si collector base is reverse bias. Okay? Basta active region. When acting as a switch, so as what I've said, puli-puli siya o switch from cutoff region to saturation and vice versa. So cutoff, saturation, cutoff, no? Bailo-bailo. So when it is in cutoff, both base emitter and collector base regions are forward bias. No? Naka-forward bias both ang base emitter and collector base regions. Whereas sa saturation, si base emitter and collector base are both, cut off mano. So cut off. So reverse bias dapat ni. Whereas kung saturation, forward bias. So how to do that, mo na itong ma-learn soon. Sa ato lang timan-an, no? Na the two main applications of or functions of an amplifier, of the transistor is amplifier or switch. No? Whether BJT or FET, we'll learn also soon na even ang field effect transistor will act as either amplifier or switch ng gihapon. So active region, kung amplifier, then kung switch, cut off and saturation and cut off. Okay? Okay. So nasa slide. As VC is increased, IC increases until B. Then it flattens in the region between points B and C, which is the active region. After point C is the breakdown region. Okay. Well, it's better ba masulot akong pag-explain earlier. No? Okay. So the collector characteristic curve illustrates the relationship of these three transistor currents, IC, IB, and IE. So the axis, no, mga axis sa atong characteristic curve, ang x-axis is VCE, ang y-axis is IC. How about the curve itself? The curve itself is IB. No? So, ang daghan manig IB. Depende kung saan operating current sa atong transistor. No? So, we'll measure it. And after measuring, example lang, no? Example. This is 1 microampere, 2 microamperes, 3, 4, 5. This is 6 microamperes. No? So 1, 2, 3, 4, 5, 6. No? Just for example lang yun. And after building our circuit, atong na-measure ang current sa atong collector, sa base to be, let's say for example, 5 milliamperes. No? So we'll use this characteristic curve. No? So ignore na din ang uban. Because ang atong operating current sa base is 5 milliamperes, 5 microamperes, sorry, we'll use this characteristic curve. So ignore na din ang uban. So if this is 5 microamperes, sorry, sir. So sa ating ganyan na 6 microamperes, 5 microamperes, 4, 3, 2, 1. Then can you see 5 microamperes? Ato na siyang itanawon kung pila ang value sa y-axis na IC. Let's say lang that this is 7, no? Milliamperes. 7 milliamperes. So 7, 6, 5, 4, 3, 2, 1. So after determining the value of our IB and the subsequent value for IC, we can now obtain the beta, no? Beta, the ratio of the collector current to base current. So beta. Another term I think for beta is DC, current gain. Well, DC current gain, beta, is equal to IC over IB. So whatever is the ratio of IC and IB, that is our DC current gain. So diyan natin ma-determine how powerful our transistor is. Okay. So what we rearrange, we'll have the second important formula or relationship that defines our transistor. IC is equal to beta IB. Okay, so that's the second one. The first one is to ganina. This one from Kirchhoff's current law. IE is equal to IC plus IB. So memorize na daan ha. The second one is this one. IC is equal to beta IB. Beta is usually constant and given, no? Usually given na siya. How do we experimentally measure beta? So using an ammeter or multimeter, we'll measure IC, then we'll measure IB, then divide natong duha, so we'll get beta. So very simple na procedures. So for example, this one, what is the beta for the transistor shown? So if we look at the example values on the right side, we have from 0 to 60 microamperes, and first first step solution is choose a base current near the center of the range. In this case, 30 microamperes. So kana kung nag-choose yun that would be very wise choice actually. You remember, we'd want our Q point to be somewhere in the middle for it to be used as an amplifier. Gusto nga ubos na pod kaayo or taas na pod kaayo dito or sobrang na pod kalayo. So maling nasa breakdown region, maling nasa cutoff, maling nasa saturation. So I think ang assumption na is use siya sa amplifier. So we have our Q point somewhere in the middle, somewhere here. Okay. So at what value of IC is that? I think nasa mga 5 milliamperes. No? So IB is 30 microamperes. IC is 5 milliamperes. Ito lang ang i-divide. 30 divided by 5. Sorry, 5 divided by 30. Ay, 5 milli divided by 30 micro. So 166 or 167 ang beta. So beta is unitless. Okay? Because ampere is divided by another ampere. Unitless gain. So muna siyang amplification factor sa current 167. So very easy if dili given si beta. But if given si beta, it's the other way around. Either si IC or si IB ang pangitaon, which is usually the case in circuit analysis. So the cutoff region is defined as such, which ako naman na-explain earlier. No? Cutoff is when the Q point is somewhere at the very bottom of our characteristic curve. Diba? Is when both the base emitter region and collector base regions are reverse bias. That's the cutoff region. Saturation is opposite. No? So I explained earlier. The DC load line. No need for this one. If we'll do a more more visual and graphical maning analysis. So kita more computational man ta. So dili na necessarily mag-use kay DC load line. This could be used for checking. So di kay siya useful kung ano tayo mga accurate and definite values. Data sheet or specification sheet na dito ang value sa beta DC, which is given as HFE. No? Medyo karaan ni siya nga term for beta, HFE. Parehara na sila. Wala pa gyapon gibago sa mga manufacturers karon ang specification sheet. HFE gyapon lang ang ginabutang nga parameter for beta. Wala, no? So BJT amplifier. So a small amount of current at the base, no, will be amplified at the collector. So more pasabot ani nga slide. So kaning mo ni siyang switch, no? This is what I have explained earlier. BJT can also be used as a switch, switching device in logic circuits to turn on or turn off. So in cutoff, dili sa visual sa silong, the transistor looks like an open switch. So cutoff synonymous to off, okay, or open circuit. Saturation, di ba? When you say saturation or saturated, it usually means na fill up na, di ba, or napuno na saturated, na saturate, so to speak, ang sponge. Na saturate na siya water, so napuno na og water na tong sponge. So when we say that the transistor is saturated, it is saturated with current, no, puno na siya og current, nabot na niya iyang maximum current, so the switch is on, no, maximum current. So pwede po natin siya shorthand as this one. So kung cut off, voltage is high, current is low. And opposite kung saturated, voltage is low, current is high. Okay, current is high because the transistor is saturated with current. So that's going siya timanan. So one practical type of BJT transistor is the phototransistor. Okay? So why did I say practical? Because most instrumentation circuits that require a proximity sensor uses a phototransistor. No? So magiging siya exactly the same as the usual transistor, but unlike lugar sa previous transistor that we have discussed, dire, we need to have an external circuit to produce IB, or the current that will go inside the base terminal. So not so with the phototransistor. The base current will be produced by the light, okay, sa base terminal. No? So muna yung symbol for the phototransistor. The same sa regular nga transistor, nga nagyapon, but nalay arrow inward, no? Coming in. So that means that this is a phototransistor, and IB will be produced by the light. Okay? Light nga ma-detect sa atong phototransistor. Phototransistor produces base current when light strikes the exposed photosensitive base region, which is the active area. Phototransistors have a high gain and are more sensitive to light than photodiodes. And phototransistors are used in conjunction with LED. So LED ni ang nasa left side. This is an LED. So sa right side is the phototransistor. Why? So the LED will produce the light that will be used to be converted to IB. So, nag-work in tandem. So, asa ni magamit? Kasi for example, very simple application. Okay? So, ato na siyang gi-connect sa sulod sa atong sa door, no? So, let's say for example, kaning LED na to is naa siya sa naka-install siya sa door frame na side, no? Whereas ang phototransistor is nasa door mismo. Okay? So, when the door is closed, meaning nagdikit si LED o si phototransistor. Meaning ang light ni LED is ma-detect ni phototransistor. So when the door is open, okay? So when the door is open, dili na ma-detect ni phototransistor ang light ni LED. So pwede, no? Nga i-connect na to ni ang atong phototransistor sa isa ka alarm system. Okay? Alarm system. PCC. Such that when the door is open, no, ma-detect niya nga ma-detect niya nga open ang door. So the alarm goes on. Well, conventionally, the alarm goes off. Tingog siya. Okay? So very simple na application, no? Very practical. Although more sophisticated man gid ang actual nga mga security systems than this. Pero pwede gid mo maka-create og inyong own nga simple security system sa inyong sa inyong room, no, sa inyong balay. So, di mo gusto nga sudlan inyong kwarto sa inyong mga igsoon, no, sa inyong ginikanan, pwede mo butang ingani. Palit lang mo optocoupler, then connect niyo sa isa ka alarm or bell. No? So na mo inyong own nga practical security system. And even industrial types of instrumentation circuits use optocouplers, no? Di naman din necessarily kita sa security nga application. Pwede man gihapon no? Sa conveyor belt, no? Sa conveyor belt. No? Maybe dili gid LED ang gigamit because LEDs produce a much weaker man nga light. Let's say for example, more powerful na light source, a laser. natay laser dire. Laser. Yan na. Yan na dire nga atong photodiode. Sorry, phototransistor. Yan na. Okay. So when there is no object sa in between the laser and the phototransistor, pwede niya i-off ang conveyor. So, or i-on baka. Don't know. Depende, no? Basta may tabo, when there's an object blocking the light from the laser to the phototransistor, kung may object diha, pwede i-prompt sa phototransistor ang isa ka motor siguro, no? Motor to turn it on so that the conveyor belt will be turned on also. Okay. Pwede yan, very simple nga kuan. Very simple nga application. Industrial application. So you could do many types of things using only the optocoupler, no? I'm not sure kung available gid ni all of the time sa itong mga local na stores. Pero, but we could create man, no? We could create our own optocoupler. Na may optocoupler nga na mapalit. Na naka-package na, no? Pero we could create our own, no? Our own optocouplers using an LED and a separate na phototransistor. These are some examples of applications for optocouplers. Traffic controller. Yeah. So these are a sample of common transistor packages. One yung pinaka-common nga through-hole na transistor na package, no? Na discrete na transistor. Siguro exactly like this one, gid kadako. Okay, nasa itong screen ka ba? Kani siya is, so siya na type ng surface mount na transistor, this one. No? I think kani heavy duty is ng transistor. Nasa mga heatsink. No? Electronic device na nagyapon ang transistor, mo init, magina siya. Just like this one, exactly like this one. Kaning part sa transistor is the heatsink. This might be an industrial na transistor. No? So, transistor is nasa sulod. So, base, collector, emitter. Base. Sorry. Yan na siguro, no? Nasa sulod sa atong kuan. Sa atong package. Okay? This black stuff is made of kuan man no? Made of epoxy naman siya. Plastic. So napasasulod ana, no? Nasa sulod ang atong actual na transistor. The transistor is not really the black stuff. That one is just a coating made of epoxy. The metal one is the heat sink. Para dali maguba ang transistor kung mainit. And mainit kina siya. Being an electronic device. So we could use a multimeter, of course. We could use a multimeter to test if our if our transistor is still working or not. How do we do that? We just place the terminals sa pins sa atong multimeter. Ang positive is nasa sakto ni siya. Dapat ani ang positive is nasa base, no? Dire. Whereas ang negative is nasa emitter. Yeah. And na tayo ma-measure nga value. And what value is that? Asa naka-point ang atong knob sa atong multimeter? Here. No? Naka-point siya sa diode. Why diode? Because ang base emitter nga region, no? The base emitter region of the transistor is just acts just like a diode, which we have discussed extensively for the past quarter, no? So because it acts just like a diode, and kung ato na siyang ibutang dire, no, in this manner, dapat na tayo ma-measure nga voltage equal to 0.7 or at least close enough. Okay, malagi siya diode. So that is now our third relationship. VBE is always equal to 0.7 volts. So have this in mind na lang yun, always. No? So we have three relationships na that define our transistor. Kung in mathematical terms, those three formulas describe our transistor. Okay? So in summary, we have three formulas that describe our BJT. Again, one is IE is equal to IC plus IB. The second one, so ito, IC equals beta IB. So pag lisod timan-an, IC is the product of beta and IB. So para sila letter B. The third formula is VBE is always equal to 0.7 volts. Last but not the least, number 4, which is just combination of formula number 1 and number 2. If we substitute formula number 2 to formula number 1, we could create this formula. IE equals, if IC is beta IB, so IE is beta IB plus IB. Correct? So IE is beta IB plus IB. So atong i-factor out si IB. So IE is then equal to beta plus 1 IB. So more ni siya ng 4 very important formulas that describe our BJT. Napay number 5, which is just an approximation. No? So di kaya na ako ginagamit. Usahay na lang kung switching ang application. No? Mag-ingon lang siguro ko og times kung sa ato ni gamito number 5, but these 4 suffice naman already. Number 5, approximately IE is equal to IC. Okay. Why? Because IE and IC are measured in milliamperes na range, whereas IB is measured in microamperes, no? 1,000 times smaller. So in switching purposes, pwede tayo magamit og fifth formula, no, for approximation, no? Pwede na siya for switching applications. For amplifying applications, pwede lang nato i-ignore ang fifth one. Basta kay kaning upat, man yung pinaka-importante. Pwede kay dili ning upat, may horizon, pwede kaning tulo. Because ang ika-upat, is just a rehash of the first and the second one. So ako lang i-draw again ang BJT ba? So na-add si 0.7. Always na siya 0.7. Okay. So NPN eh, diba? Because pagawas ang arrow is pagawas padulong kang emitter. So that is our IE. So if NPN, pasulod si collector, pasulod si base. IB. IC. So because of these formulas, notice if one is determined, all the others kay ma-calculate na dayon, no? So what if beta will be measured or will be obtained? No? Sorry, beta. IB ay. Kung what if si IB is ma-solve na or ma-calculate na. Kung follow na dayon si IE o IC. No? So, given magining beta, if ma-solve na si IB, makuha na si IC. If makuha si IC, substitute lang si IC dire, substitute lang si IB dito, makuha lang si IE. So, at least isa lang anang tulo makita na yung tanan. So that's for the currents. How about for the voltages? Again, we have 3 voltages. VBE, VCB, or VCE. VBE, no need to solve. Constant. VCE is usually the one that is solved. Or calculated. Whereas VCB is ignored. No? So di nato gayo gina-measure gid si VCB, especially in amplifier nga applications. Why? Because we assume that VCB is reverse bias. Just like what I've said earlier. Okay, so I think dito tataman, no? Any questions?